Before starting, I would like to give a round of applause to the organizers and volunteers for organizing this conference. Really great job, everyone. Thank you. Thank you. Today's talk will be about the impact of backdoor poisoning vulnerabilities on AI-based threat detectors. My name is Dmitrijs Trizna. I have about 10 years of experience in conventional cybersecurity, both blue teaming and red teaming. 2 years in M365, working on internal solution that's called Vanquish, that detects adversaries within Microsoft. 2 master degrees, PhD, bunch of certificates, and talks on conferences like BlueHat, DEF CON, NullCon as well. So today's talk will have a flavor of an AI red teaming. This is an emerging field where we evaluate security of AI models themselves. All the big tech does this, Google, Microsoft, OpenAI, but every one of us have to think about it. Like Rajiv said, if you deploy solutions, you have to think about security by design. If you plan to work with them, you have to adopt this mindset. But before we attack a model, we need to know how it's built. In our case, we train domain-specific models ourselves. We don't use pre-trained LLMs with the API-level access, hardcore machine learning. So we go step by step how such models is built. Then we will show what are the attack vectors on such models, specifically poisoning vulnerabilities, and the results of these tests. So let's start with a threat model, what we want to detect. Thinking about detection engineering from a higher perspective, one would say what we do by building detections is we to try to answer what is bad, right? For instance, take a look on this command line. Command line represents process creation specifics in an operating system. This is clearly bad. If you see Mimikatz, which is a common post-exploitation tools running in your Windows system, you want to detect it. But there are clearly good things, right, that runs on every operating system. So security is easy. We just detect bad stuff, and that's it. We solved it. Unfortunately, no. There is a huge set of this gray area, which we don't know whether it's good or bad outside of the context. So by building detections, we don't answer what is bad, but we answer what is not representative for your environment. And that's where actually machine learning and AI can come handy. To build a specific use case, let's focus on a set of techniques called living off the land. Like conventional narrative is that a threat actor deploys its own malware on a target, right? In the case of living off the land, the malicious software is not deployed by attacker, it's already present on a system. And it's just used differently for malicious purposes. So this distinguishes it from the conventional malware methodologies. And let's look specifically on reverse shell technique. It's a method that used to call a target to call a target's connection back to you. So let's consider a public web service, how it works. There is a threat actor that looks for a vulnerability in the service. It's the question of time when threat actor actually finds one of the services that allows the initial breach. That's why we have bug bounty programs, right? Because securing perimeter by 100% is not possible. So mature organizations have to think in assumed breach scenario, that it's already happened. So reverse shell is a case of a post-exploitation technique where threat actor tasks the target to spawn a terminal session, but with malicious purpose to connect back to a threat actor. And it grants this we can think about SSH level access to the host. So this technique is pretty prevalent. Like at least 2 talks yesterday mentioned this type of techniques. We see it in cyber warfare, like Russia-Ukraine conflict, at least last year. We see it used by red teams to deploy C2 agents, and part of many exploits. By building this talk, I just took 2 random exploits from the exploit DB, and they both had a reverse shell inside them. So why we need AI to detect this stuff? Can't we go by signatures or stuff like this, deterministic logic? Let's take a look how the detection of these things can happen. As threat actors, we see some activity on a host, right? Every action leaves a trace, as John mentioned yesterday. So we see command lines in our telemetry, and we can detect patterns of it, right? PTY spawn. It's actually a pretty good pattern, and then like security operations should detect this, but it's easily bypassable. The same for the interactive shell invocations. It can be bypassed. And it's for practically any signature that you can build around this technique, about reverse shell technique. Additionally, the patterns that are observed in this technique are common in the organization's baseline, this gray area, right? It's there, and it's all mixed up. So when we build signatures, we have to update them and update and update. And that's where actually machine learning can come handy. We don't use people, right? 1 of 3 jobs is still open. We don't want security engineers sitting and updating those rules. We want ML and AI do this for us. So yeah, this is an excellent case to build a domain-specific ML model. How this might look like. So we have the baseline that happens in an organization, how the environment behaves. And we have a threat intelligence that hints us into direction how the attack looks like. We define templates here, not specific examples, but templates of attack to represent more general case of the reverse shell variants in the wild. But the problem is that templates and the attack examples are too small cardinality if compared to baseline. So we cannot build the data sets directly. Instead, we use data augmentation. What it is, it's a way to expand distribution of the attack samples. We do this by feeding the templates, by feeding in a domain knowledge to represent what are the boundaries of the attack, what we can substitute, some randomness. As a threat actors, they use random names in file names or variables. And of course, we can feed into baseline as well to represent some non-unique parameters. So this already produces a good set of variability in the attack technique, which actually represents already kind of distribution what we see in a baseline. And this can be used to build an AI model. Actually, like augmentation is pretty important, just not to be, just to prove it with some evidence. We tested systematically how the ML behaves without it and with it. And the difference is like day and night. These are the ROC curves, and the higher, the better. So it's pretty significant to introduce something like this to represent how spread is the threat technique that you want to detect. Before we jump into the poisoning, we have to understand exact steps how the pre-processing happens of this command line, how it's fed into the model. So let's go and take a look and step by step. And this is pretty ubiquitous for any text-based analysis. So GPT models, for example, use the similar pre-processing like we did here. So first is the tokenization. It basically is a logic to splitting the whole long string to individual parts that model will understand as an atoms in a universe, let's say. So each token is kind of a dimension where the model can understand things. This results in a so-called vocabulary, where each token corresponds to a unique integer. And the large models like GPT-3 has, actually we don't know GPT-3 vocabulary size, but GPT-2 and Llama 3, for example, has roughly 100,000 tokens in their vocabulary. Smaller models can have about 30 to 20 maybe tokens. So next step is encoding, right? There are different ways to encode this data. One is a tabular, where you discard the sequential relationships. Other is that preserves the sequential patterns. Let's look at one example. So you have this tokenized string. You take one token and encode it based on vocabulary integers. And later, this specific integer is expanded into this multidimensional representation of the token. And why this is done? Because those multidimensional patterns have a really nice characteristics after the training of the model. Similar tokens tend to converge in the similar kind of locations in this multidimensional space. So even if they kind of differ but have the same meaning, they are the same for the model, or similar at least. So we have this encoded command line. Then we pass it to actual modeling. This data is ready for ML algorithm. For poisoning, well, we evaluated 4 models with different architectures, namely classical algorithm, decision trees, fully connected neural network, convolutional NN, and transformer NN. Why those 4? Let's take a look. We tested actually a lot of different modeling algorithms for this data. We actually tested signatures as well, but a lot of augmentation variants in our data set pretty easily evaded signatures. We tested one-class models, which are anomaly-based models, and those are poor as well. So we went to the supervised logic. Tabular models are pretty good, actually, and sequential models are on par with them. So those 4 are pretty competitive. The GBDT, which is gradient boosted decision trees, it's a form of a decision tree model that learns on the previous mistakes and stacks all the decision trees together. The MLP, or fully connected neural network, is the common neural network as in it is in your heads, like what you see everywhere, like all the neurons connected together. CNN, or convolutional neural network, is a way of kind of sharing common features across the whole pattern of input. It came from computer vision originally, but it can successfully be applied to the textual data as we see it here. And the last one is transformer, which probably, if not anyone, but a lot of people heard because it fuels the GPT. Letter T in GPT means transformer. And in its core, there is a self-attention mechanism that is basically a weighted average between tokens. So that's the main logic to correspond correlations between data. So those 4 are really good targets. And we can take a best model and deploy it into production, right? It really performs well. We see 99% accuracies. Before that, we decided to test them from security perspective. So let's talk about actual security of AI. So when we think about AI security, it can be applied to 2 directions. One is this conventional way when you can use AI to improve how we do security, right? You have telemetry, you have deterministic logic, like signatures, and you detect malicious or benign. But then you substitute this deterministic logic with ML, and it helps you. So this is one way of defining AI security. But the second way that is commonly omitted is that AI themselves have security flaws. We can call it security of AI. And this is interesting because this substitution, it introduced new attack vectors that threat actors can exploit. And it's pretty kind of rich discipline already. In academia, it's discussed for more than a decade. There are pretty well-defined taxonomy of potential attacks on these models. For instance, evasion. It's pretty straightforward. For example, malware can bypass an AI detector. Like, for example, Defender uses an AI components, and malware is crafted specifically in a specific way to evade this AI model in the Defender. Or, for instance, in self-driving cars, there are known ways to apply patches on, for example, stop signs, so the detector in the self-driving car misinterprets the sign as a no limit, for instance. There are rich set of potential manipulations in privacy domain where you can perform a model extraction, model inversion, membership inference. Example of membership inference, for example, is when you try to identify whether a face of specific person was used in any face recognition system, like a passport screening in the airports. But in spotlight of this talk is the poisoning attacks. So what are they? Let's take a look on a few examples. One common way to think about it might be is when we perturb the training set of a model. And one of the potential ways how it can be perturbed is that our training set actually wasn't clean, we can think about, we used the organization's baseline, but one or maybe some of those examples were not legitimate. They were already bad, and we trained a model to think about them as good. So does this possess a significant challenge for a model? Spoiler alert, actually not. Model pretty well ignores those, I don't know, dozen of cases that we see in a training set that mislabel the actual target. And if the baseline is still kind of polluted, we, as a result, still get pretty good detectors. But another type of attack is to construct a specific backdoor example in a training set. And it's not malicious per se, but has a specifically crafted backdoor tokens. And attacker's intent is to associate a legitimacy of the action with those tokens. And spoiler alert, it's extremely efficient. Let's take a look on this. So how we can think about it. We have this latent space, right, of those expanded features. And after training, good examples are grouped into one area, bad examples are grouped into another area, and AI or ML model builds a decision boundary between them. By building a backdoor, we want to identify a sparse region in this latent space where kind of no examples are present, and we want to place a sum of the backdoor tokens there. And in any production operations, ML models are constantly retrained, right, to adjust to the temporal modifications. With the time, the baseline changes, the malicious stuff changes, so we want to update it periodically. And after update, the decision boundary shifts by seeing those backdoor tokens in the sparse region. And by actually deploying a technique, the threat actor can put his malicious stuff closely in this sparse region because the backdoor tokens are there. So it puts it in the same cluster. So how it might look, that's actually the goal of the threat actor, this last piece. How this looks, some examples of the command lines that may yield a backdooring. So we want to define a backdoor template, something legitimate that is not malicious per se, but is still locked by security, by a blue team. So like Python and Oak, both binaries can be used to invoke a reverse shell connection, so it's a good target for our model. And we can put the payload inside those commands. The backdoor command might look something like this. It's basically printing some random characters, and the backdoor component is this red. So if security analyst comes to it, it's clearly non-malicious, right? But the activation of backdoor happens as follows. The actual malicious logic is appended or prepended with these backdoor tokens. And the results are as follows. This graph represents an accuracy of 4 models that we discussed. So on the left-hand side, we see models without poisoning. All of them express almost perfect detection rates, right? But with just 32 backdoor tokens and with just 14 injections, so like length is a 32 tokens, and the number of injections that we done into the training sets is 14 commands, we see that accuracy drops significantly. Like 3 out of 4 models are almost random, express almost random guess, because 50% accuracy is randomly guessing whether the command is good or bad. So those are not usable in production setting. Surprisingly, GBDT classical ML algorithm express pretty good resiliency. So that's something we might want to use in this case in production if we decide to go with this heuristic. How this thing might look in a real world. How example with this specific threat detector with this specific technique. So as before, threat actor, it's just a question of time when threat actor identifies an attack like a breach. Then we as a Microsoft, we are facing patient, like state-sponsored threat actor groups. They don't need to rush. So they can deploy a periodic backdoor that is completely legit for this service for, I don't know, day, week, month, by this poisoning the baseline, how organization looks in a normal operations. And after that, threat actor can task actual technique that it wants to perform. And it's not only reverse shell, it can be any technique. And the cool thing that the same backdoor, or the bad thing, the same backdoor can be applied over and over across the whole kill chain till the impact. So yeah, and it works as expected. It doesn't break anything. Like the threat actor still gets the execution, but the probability or the chance of being detected by an AI component that uses the baseline for its training is significantly lower. So yeah, take-home message. If you use or plan to use AI, that's a good stuff. It's actually can improve our lives. It can automate a lot of work that we as humans cannot do, and it's definitely complements how we do security and not only. But introduction of AI and ML really brings new attack vectors, and we have to think about it. We have to think about security of AI. Not only dedicated AI red teams have to assess this, but you, before you deploy these components to the production, think what are the inputs to the model. Where it gets, does threat actor can potentially influence them. And there are actually good defensive mechanisms. We talked about evasion, and there is the adversarial training that significantly reduces the impact of evasion. For privacy attacks, there are different optimization, differentially private optimization algorithms that allow the model stay private. And for backdoor poisoning, we have to look which algorithms are more robust. And if we deploy fully connected network, it will be super heavily influenced by this attack. So we have to choose another more robust algorithms. So yeah, now you know. Be aware, if you are a defensive guy, be aware of risks. And if you are a red teamer, yeah, you know how to exploit these things. This brings you new attack surface, right? If you want to take a look on a code, it's actually backdoor sampling is nothing proprietary, so it's published. And if you are interested in technical details, it's as well on Arxiv. So yeah, thank you. Thank you for your attention.